Welcome to Lecture 16, where we will be talking about other galaxies. In here, we'll be talking about spiral galaxies, barred galaxies, elliptical galaxies, irregular galaxies, and we'll start to talk about what's at the center of active galaxies.
There are four basic types of galaxy that scientists have determined so far, which are incorporated into the Hubble classification scheme. These include spiral galaxies, barred spiral galaxies, elliptical galaxies, and irregular galaxies. We learned some about spiral galaxies last lecture
when we learned about the Milky Way.
All galaxies of this classification have a flattened galactic disk containing spiral arms, a central galactic bulge, and denser nucleus, and an extended halo of faint old stars. Basically, when you turn it sideways, it looks almost like you have a flying saucer. When you look at it head on, you essentially have the circle, and it's surrounded by all of these arms, which gives it the name spiral galaxy. It appears to spin in a spiralizing formation. Basically, what we have in the center is it's really hot. It's where we're going to have our supermassive black hole. We're going to have a lot of new stars being formed there, as well as in the rings itself. And then out here, we essentially have a halo of old, very old, faint stars. The stellar density, or stars per unit volume, is greatest in the galactic nucleus at the center of the bulge, which is right here. By the Hubble space scheme, spiral galaxies are denoted by the letter S and are classified as type A, B, or C, which is based on the size of the central bulge. SA galaxies have the largest bulges, and SC have the smallest. SA galaxies tend to have tightly wrapped, almost circular arms. SA are going to have the most tightly wrapped of the arms. They're going to have a very large bulge in the middle, whereas SB have more open spiral arms here, like we can see here. You can tell here they have a smaller bulge, and then we get to SC, which has an even smaller bulge, and we have much looser arms here than we did here versus here, where we can even just tell the tightness that they're getting. Barred spirals are very similar to spiral galaxies. These galaxies exhibit a bar of stellar and interstellar matter passing through the center and beyond the bulge, designated by SB, and are also subdivided into A, B, and C based upon the size of their bulge and spiral tightness, correlating with the bulge size. What you're able to see is here's our central bulge, here is the bar. It literally makes almost like a bar through the center, which then becomes our spirals. SA looks a lot like a spiral galaxy, very tight arms, bigger central bulge. SB, we have a much smaller bulge. We can see how the spirals are starting to become more like an S shape, like elongated, rather than here it looks like an E shape. Here we're starting to see this kind of shape versus here where we're seeing a mathematical term that I don't remember the name of. Anyway, you can see how they get progressively smaller in the galactic center, and their spirals tend to get more pulled out. Elliptical galaxies have no spiral arms and no disk, but they come in many, many sizes, from giant ellipticals of trillions of stars down to dwarf ellipticals of fewer than 1 million stars. Ellipticals also contain very little, if any, cool gas and dust, and show no evidence of ongoing star formation. Many have large clouds of hot gas extending far beyond the visible boundaries of the galaxy. The Hubble type depends on its intrinsic 3D shape and on its orientation relative to line of sight, and is designated an E. Classification ranges from E0, which means it's pretty much spherical, to E7, which means it's more of elongated, more of an oval. This is subdivided by how elliptical they appear in the sky. So what we have here is E0. It looks pretty much like a sphere. By E4, we're getting more of an ellipse shape. And then E5, we have even a further ellipse shape. So you can guess by E7, it's really elliptical. Elliptical galaxies sometimes form the biggest galaxies we see in the universe. However, they also are majorly dwarf galaxies. When an elliptical galaxy is between E7 and SA, there is evidence of a thin disk and flattened bulge, but no spiral arms. These are designated S0 if there is no bar, and SB0 if there is a bar. So in this case, we can kind of see a bar here, making it an SB, and this one is just a flat disk with that orb in the middle, making it an S0. This final galaxy, irregular galaxies, is a classification that was intended as a catch-all by Hubble. These galaxies are irregular because, well, their visual appearance excludes them from any other category. They tend to be rich in interstellar matter and young blue stars, but lack regular structure. They tend to be smaller than spirals, but larger than elliptical dwarfs. And as with elliptical dwarf types, irregular galaxies are the most common. There are two subclasses here that we got, Irregular 1 and Irregular 2. Irregular 1 looks like a misshapen spiral or Magellanic cloud, and Irregular 2 are much rarer and they have quite a few peculiarities with them. They have distinctly explosive or filamentary appearance. Basically, it looks like it blew up. At first, astronomers thought it was due to a violent event, but now it is believed to be due to a close encounter of the third kind, or a collision between previously normal galaxies. Basically, what they think is that Irregular 2 galaxies are the result of two galaxies colliding. What we have here are Irregular 1 galaxies, which I said earlier, literally previously, that look like Magellanic clouds, which is this. So if we looked at A or B, this is what it would look like close up. You can see we have a lot of bluer stars here, and then we have larger Magellanic cloud looking things, which is picture C, which looks like this. And they're quite beautiful. They have a lot of different colors. You have whites, blues. They're much prettier, and they look a lot more controlled and organized than Irregular 2 galaxies. So here's what an Irregular 2 looks like. We can see this filamentary appearance where it really looks like it kind of exploded. It really shows how unique galaxies are and that we can't predict them. Over here we have another Irregular 2. Again, this is what happens when they think normal galaxies, probably of about the same size, collide, and they're going to essentially rip each other apart. Some galaxies are going to pull material one way and then other material is going to pull the other. Over here we have the table of galaxy properties. This is essentially a sum up of everything that we had on previous slides, all in a lovely organized fashion. So if you want something to study from that'll make it a little bit easier for you, here you go. Determining how far away other galaxies are from us is very important. It allows us to figure out not only how fast or how far apart we are from other galaxies, but how fast the universe is expanding, how far it may take for us to even visit these other galaxies, should we ever be able to leave our galaxy. The method of using Cepheid stars only allows scientists to see about 25 megaparsecs from Earth. Many of these galaxies are actually beyond that. Now we need to find a new way. What would be a good distance determiner? One of these is to use standard candles, which are bright, easily recognizable astronomical objects whose luminosities are confidently known. Once an object is identified as a standard candle, which has to be due to its appearance or shape of light curve, its luminosity can be determined and compared with apparent brightness for the object's distance, and so the distance of the galaxy it lives on, so on and so forth. This is very similar to how Cepheid variable technique works. The most useful standard candle has a well-defined luminosity so that uncertainty in estimating its brightness is small. And 2, it must be bright enough to be seen at great distances, basically greater than 25 megaparsecs from us right now. Examples of reliable standard candles are type 1a supernova and planetary nebula. Supernova can actually be seen from a distance greater than 1 gigaparsec. And I know you're thinking, well, supernova, once they're done, aren't they done? You have to realize that it takes a long time for us to be able to see these changes. So supernova will last in the sky for a long time because not only do they just explode, but sometimes they leave behind this cloud, which becomes a star nursery, which is where we get nebula. A second method was determined in the 1970s when astronomers discovered that there was a close correlation between luminosity and rotational speeds in spiral galaxies. Rotational speed is a measure of the total mass of a galaxy, just like a star. And this has a very close correlation with a galaxy's luminosity. And this is known as the Tully-Fisher relation. It allows us to obtain a remarkably accurate estimate of a spiral galaxy's luminosity from its rotational speed. When luminosity is compared to the apparent brightness, scientists can then ascertain its distance. This can be used to measure distances of spiral galaxies up to 200 megaparsecs from our location. The rotation speed is determined by looking at the star's frequency and its Doppler shift in reference to its spin, which is cool. As the spiral galaxy is spinning towards us, we're going to have blue shift. When it's right about here in the middle, it's going to have its normal frequency unshifted. So let's say it's normally yellow, versus when it's going away from us, it's going to stretch, so it will be red shifted. And so with a combination of all these wavelengths, we can figure out how fast it's actually spinning and then use that to help determine its luminosity. A similar method is used to measure the diameter of elliptical galaxies, which is using Doppler broadening. Once the galaxy's diameter and angular diameter is known, its distance can be determined using geometry. Faults with this is that the errors from other distance measurements, which are used to help determine farther and farther stars, actually accumulates, meaning if star 1 has a little bit of an uncertainty, that's going to be added together to the next uncertainty and added to the uncertainty after that and after that and after that. So you end up with this buildup of uncertainty. So you can go from being plus or minus 1 light year, let's say, to, let's say, plus or minus 250 light years, which can be a big difference in trying to figure out how much of an error you have in your calculation. But the result is in the farthest stars and galaxies from us being the most uncertain and so the least well known. Groups of galaxies can make up local neighborhoods and are generally held together by their gravitational attraction, and this is known as a galactic cluster or a galaxy cluster. Our galaxy cluster is known as the local group, which is a group of galaxies that make up our galactic neighborhood. Local groups are about 1 megaparsec in diameter. Ours happens to be made up of Andromeda, M33, and the Milky Way, which are our spiral galaxies, and then the numerous dwarf, irregular, and elliptical galaxies, making a total of 55 galaxies in our local group. A galactic cluster or galaxy cluster is a group of galaxies held together by their gravitational attraction. And then after that, you get superclusters, which is lots of galaxies coming together. A nearby galaxy cluster is the Virgo cluster. It is much larger than our local group. It contains about 2,000 galaxies. The Virgo cluster is made up of about 50 local groups, making it a massive supercluster. It is about 30.66 megaparsecs in diameter. So I want to make this clear. When you have enough local groups or galaxy clusters together, you end up with a supercluster. In 1912, Vesto M. Slipher, which was an American astronomer, determined that almost every galaxy he had observed had a red shift to it, meaning they were moving away from us. With the exception of a very few nearby galaxies, every galaxy is part of a general motion away from us in all directions, including galaxy clusters. The image here shows the optical spectra of some galaxies that are ordered from least to most redshifted, and this is known as Hubble's Law. The redshift can be plotted comparing recessional velocity against distance, which we can see on the right. These plots are based off of the images from the previous slide, and galaxies within about 1 million parsecs of Earth. Plots like these were first made by Edwin Hubble in the 1920s, and so bear his name as Hubble Diagrams. As the data points fall along a relatively straight line, this indicates that the rate at which a galaxy moves away from us is directly proportional to its distance from us, and this is known as Hubble's Law. The universal recession described by the Hubble diagram is called the Hubble flow. This indicates that space itself is expanding, and so the largest distances between galaxies, for example, are continuing to in fact grow. The relationship is characterized by Hubble's constant, h0. So remember we said that it generally makes a line or flow. The slope of this line is Hubble's constant. The recessional velocity is equal to Hubble's constant times distance. The value of Hubble's constant is approximately 7 kilometers per second per megaparsec. Measuring distances using Hubble's law, works better the farther away the object is, and the random motions of galaxies within clusters are in fact overwhelmed by the recessional velocity. Hubble's law allows us to then measure distances up to 100 million parsecs. I want to go over what we just heard last slide a sec. Within a galaxy, within a galactic cluster, remember everything's held together by gravity. And we're saying that a galactic cluster is moving away from us. Well, within that galaxy, those galaxies are moving on their own away from each other, but still within contact with each other because they are all gravitationally bound. So we've all heard of lightning bugs or fireflies, and even though some of you may not have seen them in real life because they're starting to go extinct in Florida, you've probably seen them on TV or if you've traveled just a little bit north. If you were to put a whole bunch of fireflies in a jar and tighten that lid real quick, you'll let them out after, promise. But if you were to put them in a jar, they would all move in their own erratic way, right? If you were to throw that jar up in the air, those fireflies are now continuously moving away from you all together as a cluster, even though within their cluster they're moving every which way that they want to. Overall, they're moving away. That kind of helps explain the idea of a galactic cluster moving away from you while the galaxies may be in fact moving towards us. Galaxies that fall within the Hubble classes are called normal galaxies, and these are our active galaxies, which are galaxies that have higher luminosities and are brighter. Normal galaxies. Galaxies that fall within Hubble's classifications. They peak in wavelengths that we can observe, like this, i.e. in the visible spectra, they have their peaks. Whereas active galaxies are a little bit stranger. They have higher luminosities. They're much brighter. They cause their spectra to differ significantly from said normal galaxies. And they have abnormal activity related to violent events occurring in or nearby their galactic nucleus. Basically, they have very active galactic nuclei. In the graph here, we can see normal galaxies peak at the wavelengths we can see, so the visible frequency, whereas active galaxies do not actually have this peak. They kind of just flow along doing their thing. The brightest among them are known as the most energetic objects of the known universe to our perspective, and all represent important phase of galactic evolution. Basically, the radiation wavelengths from active galaxies are inconsistent with what we should expect from a group of stars, so their radiation is called non-stellar. Many luminous galaxies with non-stellar emissions are called starburst galaxies, previously normal systems currently characterized by widespread episodes of star formation. There are three major types of galaxy that we will talk about: Seyfert, radio, and quasar. Seyfert galaxies resemble normal spiral galaxies, but their cores are 1,000 times more luminous. They have rapid variations in their luminosity of Seyfert galaxies, which indicate that the core must be extremely compact. Spectral lines have many similarities to those seen towards the center of our own galaxy. The lines are broad, but most likely indicate rapid internal motion in the nuclei. Energy emission from the nuclei varies over time. A Seyfert's luminosity can double or half within a fraction of a year. These rapid fluctuations in luminosity lead us to conclude that the source of energy emissions must be quite compact. Basically, an object can't flicker in less time than it takes for radiation waves to cross it, so the region must be less than 1 light year across. Radio galaxies emit very strongly in the radio portion of the spectrum. They differ from Seyfert galaxies not only in the wavelengths they radiate, but also in appearance and in the extent of their emitting radians. Radio emission is released from huge extended regions called radio lobes, roundish clouds of gas spanning about half a megaparsec, lying beyond the visible galaxy. The radio lobes of the brightest radio galaxies emit roughly 10 times more energy than the Milky Way galaxy. Bright radio galaxies are among the most energetic objects known in the universe, allowing astronomers to study the connection between the small-scale nuclei and the large-scale radio lobes. Not all radio galaxies have obvious radio lobes, though some are actually more core-dominated, where the energy is emitted from a small central nucleus, which is less than 1 parsec across. In others, you have these gigantic lobes like this, where that is also where most of their energy comes from. Radiolobes are roundish clouds of gas spanning about half a megaparsec, lying beyond the visible galaxy, which is here, and this is the end of the visible galaxy. They are super neat. Weaker radio emissions will come from an extended region surrounding the nucleus. Most likely all radio galaxies have jets and lobes, however, what we observe depends on our perspective. When we observe a radio galaxy from the side, we see the jets and lobes. However, if a weak jet fails to escape, or if we view it from head-on, looking through the lobe, we see a core-dominated system. Location, location, location. Perspective is everything. Our precise location in relation to the jet can also create a different view. It affects the type of wavelength we will actually be able to observe. The theory of relativity tells us that radiation emitted by particles moving close to the speed of light will be concentrated or beamed in the direction of motion. So if the observer is directly in line with this beam, the radiation they receive will be both intense and blue shifted, allowing for the observer to see X-ray and gamma-ray wavelengths. And this is known as a blazar. These jets are present in most active galaxies. And then we get to quasars. Quasars are quasi-stellar objects. They are star-like in appearance, but have very unusual spectral lines. Over time, scientists actually realized that quasar spectra were, in fact, normal, but enormously redshifted. And I mean enormously redshifted. Solving the question of the unusual spectra led to a very different mystery. Despite their impressive optical appearance, these faint, quote-unquote, stars, with the amount of redshift that they went through, if you go backwards, they are the brightest known object in the universe, with a luminosity of 10 to the 40, making it a W class, like a black hole. This all leads to the question, how do they produce their energy? Why is the radiation non-stellar? And what is the origin of these jets and radiolobes? Okay, so active galactic nuclei have some or all of the following properties. High luminosity, greater than a normal galaxy. Non-stellar energy emission, meaning it's not explainable by the combined radiation of the stars that are present that we can observe. Variable energy output, so it must have a small nucleus. Jets and other signs of explosive activity. Broad emission lines, indicating rapid rotation. And often the activity appears to be associated with interactions between galaxies. The accretion disk of a black hole is very efficient in converting infalling mass into energy, i.e. electromagnetic radiation. As much as 10 or 20% of the total mass energy of the infalling matter can be radiated away before it crosses the hole's event horizon. This is the event horizon. It is the point of no return. Jets appear to be a common feature of accretion flows, large and small, and consist of material blasted out into space and out of the visible portion of the galaxy. The leading theory for the energy source in these active galactic nucleuses are these black holes we just talked about. The strong magnetic field lines around the black hole will channel particles into jets perpendicular to the magnetic axis, which is how they get jettisoned away, forming these lobes. Basically, the accretion disk creates a massive magnetic field, which is so cool. So cool. It is literally a particle accelerator. Thus, the energy emission we see is due to the accretion disk surrounding black holes. It spans a broad range of wavelengths from infrared to X-ray. It accounts for the spectra of some of the active galactic nuclei that we see. High energy radiation is recycled as it leaves the accretion disk in dust and gas clouds surrounding the accretion disk itself, such as here. In many cases, the high energy radiation emitted from an accretion disk is reprocessed or recycled. Basically, it's reabsorbed and re-emitted at infrared wavelengths by dust surrounding the nucleus before reaching our detectors. Basically, super interstellar reddening. Many researchers think this dust and gas is found around the accretion disk in a fat donut-shaped ring. So depending on your location, depends on what wavelengths you observe. If you're above, you're going to see X-ray, gamma ray. If you are here, you are going to see radio and infrared. Particles, as they move within the magnetic field lines, as they're being jetted out, will emit synchrotron radiation. This radiation is actually non-thermal, but its intensity will decrease with increasing frequency, and allows for an explanation of the overall spectrum of radiation received from these active galaxies. And this is the end of our lecture, Other Galaxies. I hope you have enjoyed learning about the different types of galaxy types, elliptical, irregular, and spiral. I hope you enjoyed learning a little bit about black holes. We're going to be covering this a bit more in our final lecture, which is our next lecture. And I hope you guys all have a great day, and I will see you guys next time.